were talking about in the previous class, lecture 7, we were talking about these kinds of fin arrays. So this is the arrangement, and for this arrangement, we considered two kinds of arrays, one with small spacing, another one with large spacing. Now, first we looked at the small spacing channel. Here the idea was that the spacing is such that within a short distance from the entrance is from the bottom, the boundary layers will merge together and you will get fully developed flow. Remember one more thing, it's natural convection. So for this case, we derived some expression which gave us QF, which is the heat transfer. And we saw that QF is proportional to Z squared. Z is the spacing between two fins. So this is a fin array with small spacing, and as long as the spacing is small, QF is proportional to Z squared. Now, at the other limit, we also have large spacing channel. So large spacing channel is one where the boundary layers are kind of separate. So if you have these two fins, flow going like this, each one will develop a boundary layer, right? If the spacing is significant, then the boundary layers will not merge easily. So maybe the height is such, height of the fins is such that within the height of the fins, the boundary layers do not merge. If they do not merge, we can say it's a large spacing channel. So the point I'm trying to drive at is a small spacing, a large spacing actually show the development or non-development of fully developed flow. In this case, the flow is not fully developed in the large spacing case. Small spacing case, it's fully developed. So in this case, we had an expression for Nusselt number, and that depends on the Rayleigh number. And we could write using all this a QF large, large spacing, which is proportional to 1 over Z. Right. So this is a repetition from last class. And what can be done is that you plot these expressions. This is for the small spacing case, this is for the large spacing case. And if you equate the two, then the optimal fin spacing turns out to be this much, 2.3 times Rayleigh number to the power minus 1 by 4. Okay. And this is based on the procedure which is given in the book. There's a paper by Bar-Cohen and Rosenau. So they obtained Z optimum by L as this thing, which is similar to this one, but not exactly the same. So this is 2.3, this is 2.714. Okay. Now let's just think about what's happening here. I mean, anybody can use these correlations and derive this, but let's physically think about what is happening. So if you have this fin array with small spacing, right? So there are multiple fins, right? So if you take a front view of that fin array, then you will see multiple fins. Each fin thickness is that small t, and we are assuming that the thickness is small. Right? Just intuitively, if I make this spacing, this is a spacing is z. If I make this z very small, then is it a good thing or a bad thing? If you make z small, then you have more number of fins, okay? Because this is some area on the wall. Let's say this is your heated surface, and this is some area on the wall on which you are allowed to place fins. So the question that I'm asking is, if we make z very small and have large number of fins, is that a good thing? Good and bad with respect to which criterion? What should be the criterion? something good should give you, ultimately, what do you want this fin array to be able to do? Louder, louder. Dissipate more heat. Okay, the rate of dissipation should be larger, right? So that's a good thing. If you can get that, that's a good thing. But the question is, if you have very large number of fins with very small spacing between them, is that a good thing? No? Okay. What's the reason? Very closely spaced fins. Is that a good thing? Without looking at the equations, just try to think about what might happen. Yeah. So it will be difficult for the air to move. Like if you keep two things very close to each other, that's a bit problematic, right? Now, uh, let's think about for a minute. Let's think about why this natural convection thing takes place, right? So if you have this wall, right, and this is heated, why should the air go up? I mean, it doesn't have a mind, right? That air doesn't have a mind. Why should it decide to go up? I mean, who is forcing the air to go up? So for a minute, I'm not talking about this. I'm just talking about one surface, right? This is heated, 70 degrees Celsius. Air is at 10 degrees Celsius. We know that there will be a boundary layer and the air will go up. We know that because we've read it in books. But why? Density difference, right? So there's a buoyant force. Hmm. So this is like close to this. There's a boundary layer. Within the boundary layer, the air is lighter. Outside the boundary layer, the air is heavier. Okay, because it's at a lower temperature. This will start a mechanism. There will be flow. I cannot discuss these things in great detail because, as I said, it's not a fundamentals kind of course. So I'm just looking at some. Essentially, my target is to get practical results like this. Okay, but okay. So buoyancy will push this. Density difference, buoyancy will push this. But will something also oppose it? In nature, uh, if there is a force doing something, there is usually an opposing force. You've seen that, right? So, does it have an opposing force? Mhm. No, no opposing force. Nothing. Gravity helps in buoyancy, right? I mean, there will be viscous effect also, fluid friction, which will try to see this fluid is trying to move up. So if it is trying to move up uh, next to the surface, there are slow moving layers of fluid, and the layer of fluid right next to the wall is actually at zero velocity. So they're trying to drag this fluid downwards. So there will be viscous effect, correct? So the buoyant forces are trying to push this up, and there will be viscous effect which will try to bring this fluid down, right? So if you have too many of these channels, then the viscous effect will become quite strong, and this will become more problematic. Okay, so what we understand is very small channel spacing is not such a good thing, correct? And if we make if we increase the channel spacing, this channels the spacing that I'm talking about, okay, large spacing, then what happens? Is that a good thing or a bad thing? Mhm. If we just think about one channel first, then we'll think about multiple channels forming an array, right? So if you have channel with a large spacing, then as I said that this will give you one boundary layer, this will give you another boundary layer, and they will meet after a long distance. Ultimately, they will have to meet, but the height of the fins are such that they don't really meet. So mostly you get entry uh, entry length kind of behavior. So this is the fins form duct, right? And in a duct, you have, let's say we just talk about one channel, one horizontal channel forced convection, which you're familiar with. Okay, this is natural convection, but I'm bringing up forced convection to remind you that at the entry region, the boundary layers go like this, and ultimately after they merge, we get fully developed flow, right? And the heat transfer in this region is actually higher or lower than here. This is a fully developed heat transfer. Let's say laminar flow between two plates. Which heat transfer coefficient is higher? So there is an entry length. You're all familiar with this. You even know how to calculate entry length. So in the entrance region, there is some heat transfer coefficient. The later part, there is some other heat transfer coefficient, isn't it? So which one is higher? Hmm? Entrance region. Entrance region, heat transfer coefficient is higher. Do you have any logic for that? Again, as I've been saying, you should answer in full sentences. You just say velocity gradient. But answer in a full sentence so that I understand what velocity gradient is doing. Hmm. Normal resistance is less. Why? Okay. Think about this at home and then let me know in the next class if you're not clear about it. But the brief answer is that the boundary layer is thinner here. If the boundary layer is thinner, then the heat transfer coefficient will be higher. So this is the clue. This is not the complete answer. So you try to analyze this at home, think about it, and then you will understand. Okay. So heat transfer coefficient is higher in this region. Then the heat transfer coefficient will taper off. So if you have flow in a duct, post convection, heat transfer coefficient should go like this. Okay, something similar happens in these channels also, even though this is natural convection. This is not, this is post convection, this is natural convection. Not exactly the same thing, but the boundary layers are thinner here, so that will give you higher heat transfer coefficient. Okay, so if the distance is large, then each fin surface like this acts as an isolated vertical plate. Okay, and the heat transfer is typically good. Okay. Now, what we will say is that if the distance is really small, the flow gets affected. If the distance is large, then for that channel heat transfer can increase. But if you make the distance quite large, then you lose on the area, right? Because the number of fins, number of channels, hence the number of fins will also decrease if you have large large spacing, correct? This is what Amila was saying some time back. Okay, so there will be an optimum. So how do you get an optimum? The way you get an optimum is like, okay, you have two fins which are very close to each other. You don't like that, and you try to increase the distance. At one stage, the boundary layers will start to separate out from each other, and you will get more isolated boundary layer. But you don't want to go to that level, because then the number of fins also you are losing. Okay, the number of channels is also coming down. So you stop where it just becomes large enough. Okay, right? Not too small, not too large. So the way to do that is we say that there is a QF for small spacing, there is a QF for large spacing. You equate the two. We already have expressions for these, and if you equate the two, then you get a Z optimum, right? You already have these expressions, correct? Because we did individual derivations for Q of small and Q of large. That gives you this, right? And I just want to show you something else. I had shown you in the last class that this is from another book. This is from the book by Bejan, and here instead of Z he uses the D, and Q, the heat transfer, is proportional to D squared for small channel. For large channel, Q is proportional to 1 over Z. And what he did was he just takes the point of graphically from the point of intersection. Okay, graphically from the point of intersection, he determines the optimum value of Q. All right. So this is the approach. Now this we have done for natural convection situation. Now some of these fin arrays will operate also when you have forced flow. So there is a forced convection cooling. Now the array looks like this, and there is a forced flow. The flow is I mean, the fins go up vertically, but the flow is perpendicular to that. The flow is going in the horizontal direction. So again, we'll ask the same questions. What is the optimum spacing? This course, as I told you, this course is like, it has got some fundamentals, it has got some design, and it's also got some optimization. So this is again an optimization thing. So in this case, you have these channels. Each channel looks like this, and then you have this flow. Right? So if you have a view of these channels from the top, you will see something like this. And let's say the spacing is small. Now we will first write the momentum equation. This is familiar to you. This is x momentum. X is which direction? X is the direction which is the flow direction, basically. This is a channel consisting of two parallel plates. This is the flow direction. So you can say this is x direction, and in this direction the velocity is actually u, right? Now we say v equal to 0, del u del x equal to 0. What's the logic? Again, small channel mean that you can get fully developed flow, right? So very similar to the natural convection case. And then we write v equal to 0, del u del x equal to 0. So this term goes, this term also goes, and u is a function of y. So this is the y direction, and in that direction velocity will of course change. Velocity will be 0 at the plates, and at the central plane the velocity will also be the maximum. So these things are okay, and u as a function of y, we will say that del p del x is some delta p by L. So we'll assume that there is some delta p here, which is the same for all fins. Sorry, not fins, all channels, all individual channels, and that divided by this dimension is what? This dimension L. Okay, this is L. So delta p by L. Now this is del left hand side is 0, so we write delta p by L as mu del 2u del y2, because del 2u del x2 can be neglected in comparison to del 2u del y2. That's the boundary layer approximation, correct? So again, this is this dimension is, what are we calling this dimension? This is z. Okay, so u at z by 2 is equal to 0, and del u del y at uh, y equal to 0 is also 0 because of symmetry. This is called symmetry, right? So the average velocity is given by this. We were doing something about average velocity in the last class also, right? So the average velocity is integral u dA divided by area, and then you get this as a u bar. So expression for u is obtained by integrating this, obviously, subject to the boundary conditions at the wall and at the central plane, at the mid plane. Okay, so this is u. You place the expression for u here, and you can write appropriate expression for dA, right, by taking some horizontal slice somewhere in terms of a dy, right, and then integrate in terms of y to get this u bar. Okay, this I trust you will be able to check on your own. Again, it's the same advice. You can copy some of these expressions on your notebook and then leave some space and fill up those spaces at home by completing all the derivations, all the intermediate steps. Now, we are interested obviously in QF value for small spacing. So that is just m dot Tp T naught minus T infinity. So this is T infinity, and this is T naught. What is T naught again? T naught is also this temperature of the wall. Where is this coming from? This is like remember that this one is like this channel which you're looking from the top, correct? And we are saying that this thing, which is a fin, everywhere is at a temperature of T naught, right? That's obviously an approximation. Fins will typically not be at the same temperature. We know that shows the fin shows the temperature change like this. You know, it's higher temperature at the base and it comes down, but we are making an assumption. This is T naught. Okay. So what happens is the fluid enters at T infinity, but then once it traverses the channel, it reaches the temperature of T naught. That's also an assumption. So in a lot of heat transfer problems, we make these approximations weird because we have to approximate something. You know, you cannot say that we don't know the temperature. You have to work with something, right? So the only thing that you can work with is what are the temperatures? What are the temperature things that we know? One is T infinity. Other has to be T naught. You don't know any other temperature, right? So you say that okay, it's getting sufficient length, so it will enter at T infinity, but it will get heated to T naught. Right. So it uh, goes to T naught. Now m dot is rho, then there is an u bar multiplied by area. So this, what is this one? What is W by Z, if anybody remembers? Number of fins, right? Multiplied by ZB, which is the cross-sectional area. So this thing where my pointer is, it's the total area, right? So rho u bar A. And if you do all that, then you get m dot. And m dot Cp T naught minus T infinity will give you this. So leaving other things aside, we can see that Qf small is proportional to Z squared. Right? And we'll do one more thing. Like in the previous case, we also work on the large spacing channel. And in the large spacing channel, we can directly use the Nusselt number correlations. In the previous case, we didn't use any Nusselt number correlation because we tried to, we know it's fully developed flow, so we could get a solution for the velocity. From that, we could get an average velocity. From that, we could get an m dot, then m dot Cp delta T, that's a heat transfer. That was the approach. But here, since the boundary layers are isolated, they're not mixing with each other. So it's not fully developed. So what you do is just take a Nusselt number correlation for a vertical plane. Okay, so just use that, and that so that was what we did for natural convection. Here the correlation will change, and the correlation will look like this. So anybody recognizes this correlation? This is for post convection. So this is a flat plate, forced flow over a flat plate. The local Nusselt number is given by 0.332, etc. I think you'll remember this, right? And this is not 0.332 because it's the average value, right? It uses an average heat transfer coefficient. It gives an average Nusselt number also. So that's 2 times the average heat transfer coefficient is 2 times the local heat transfer coefficient. So that 0.332 gets multiplied by 2, and then you get 0.664. And this is valid for Prandtl number greater than 0.5. What's the Prandtl number for air? Air will be the typical fluid in these situations. So air, what is the Prandtl number? Hmm? if you have to do this thermal design course, you have to have some idea about the numbers. As I said previously also, that let's say thermal conductivity, copper is 400 watt per meter Kelvin, aluminum is about 200 watt per meter Kelvin. If you take stainless steel, maybe it's about 15, 17 watt per meter Kelvin, things like that. So similarly, here also you need to know a few things, like some numbers you need to know. Okay, so air is like room temperature, air is about 0.7 Prandtl. And of course, it's temperature dependent because Prandtl number is what is Prandtl number in terms of individual properties? Hmm? No, Prandtl number doesn't have heat transfer coefficient. Prandtl number is a property of the fluid, but in terms of individual quantity, individual property. Hmm? Okay, it's like this, right? Well, so nu is mu by rho, and alpha is k over. Alpha is k over rho Cp. So mu Cp by k. All right. Fine. So we got this Nusselt number, which gives you H. And from that H, we can get the heat transfer. So that is H bar multiplied by surface area multiplied by T naught minus T infinity. So you can get QF large like this using this and this. So that gives you this expression for QF large. Okay. And then we also have okay, so let's remember this one. This has got U infinity and all that. U infinity L by nu. This is the kinematic viscosity, correct? This has got thermal conductivity of air. We are assuming it to be air. This fluid which is being forced into the channel, we are taking this to be air. So we got this. Now, what do we do with U infinity? We will write it in terms of something else. So to do that, we use an average shear stress. So we use this expression. Can you take a look at this and see whether you understand this? So if it helps you, let me draw the geometry, because the geometry is kind of like this. This is Z, of course, and this is L, correct? And what's the height? The height is B, correct? So the flow takes place like this. So in the flow direction, the length is L, correct? So just drawing like this. This is the flow direction in which it's L, and this is Z. Right. So with this geometry information, tell me whether this is okay. Everybody remembers what is W? W is another thing that I did not mark. W will be uh, the width basically. So W is this thing. There are multiple channels obviously. W is this thing. Okay. So again, this one, is it okay? This is nothing but you just need to visualize these areas and flow direction. Then it's easy. Right? What is the left hand side? So it's got a shear stress, not the local shear stress, but the average shear stress. So that's why it's tau bar. And what is 2BL? What is BL? BL will be, see, like this is B, this is L. So this is the area which the fluid is seeing, but there are two of them on the right hand side as well as on the left hand side, correct? What is W over Z? We know. Okay, and what about this one, right hand side? Delta P times area. WB. What is WB? WB is like the area which this whole flow is seeing at this face as well as the back side, right? WB, W times B. Okay, so these two things are equal. Now, this tau, this correlation you have seen in undergraduate, isn't it? This can be derived, in fact. So, not exactly a correlation. So, this is 1.328. Hmm? And the definition of this coefficient of friction is the shear stress divided by half rho u infinity square. So, shear stress divided by the kinetic energy. And from this, you can get u infinity like this. Just from here, so the 1.328 comes in the denominator. And this u infinity will be utilized here. This is what we are targeting. This is QF large. This is the heat transfer of a large spacing. And once you do this, then you get something like this. QF large is proportional to, according to whatever we have done, z to the power minus 2 by 3. All this is again uh, from the book by Lee. So this is, I think this is chapter 2 only. The book by Lee. Now, what should be the next step? What are we trying to do? We're trying to get the optimum spacing, isn't it? We will again equate these two, QF small and QF large. I kind of told you the logic. You have to play this logic in your mind a few times. If fins are too close to each other, spacing is too small, then the flow it doesn't is not very good. If they're very far apart, okay, for individual plate, the heat transfer is improved. But the problem is then you have too few fins. The area actually comes down. So the optimization is for the total heat transfer from an array, not from one channel. It's not one channel optimization. It's for that whole array, which has got multiple channels, right? So that we are doing for small channel array and as well as large channel array. Okay, so think about this approach. It's a nice way of getting the optimum by using physical reasoning. Right, now let's see this one. This is QF large and QF small. If they're equated, then you get Z optimum by L as something like this. And what about the heat transfer corresponding to that situation? So that heat transfer is optimum because it gives you the maximum possible heat transfer, right? For the whole array, isn't it? Actually, I don't have the plot for forced convection, but it's something similar to what we got for natural convection. So it's kind of like the heat transfer becomes a maximum around here when these two things are equal, right? There is a similar plot in Bejan's book for this forced convection situation also. But I think I kind of forgot to copy it from the book, from Bejan's book to my presentations. But they essentially look something similar to this also. Of course, the dependencies are kind of different in this case. There is z to the power minus 2 by 3 and all that. Yeah, this is QF large is z to the power minus 2 by 3. And QF small is z squared in this case. Right? What were the dependencies for the natural convection case? Natural convection QF small went with that was large, right? So it was z squared. So here also it's z squared. But for natural convection, for large spacing, the heat transfer went with 1 over z. Here it's little different. So it's here it's z is 1 over z to the power 2 by 3. Okay, but same approach, and we once we have got z optimum, we can use that in the QF small expression, or we can use it in the QF large expression, whichever, to get the heat transfer, to get the that maximum possible heat transfer, right? So that we get this. And pressure drop can also be estimated. So the pressure drop is something like this. This is familiar. This one. So the head loss due to pressure drop is FL U infinity squared by 2 GD, correct? And to get delta P, you have to multiply it, but you have to make it GH basically. So you have to multiply it by G, correct? So that's the expression that you get here. Now, just again for simplification, see what is F? Small f? Friction factor, isn't it? So this friction factor, and then this is L is a length scale, then there's a DH is hydraulic diameter. So we don't know what these values are, but it's kind of like of the order of 1, we can say maybe. So just for simplicity, we are calling it FL by DH approximately equal to 1, right? And once you do that, then you get rho U infinity squared by 2, and that uh, we already have something on U infinity, so that's how we can calculate delta P. And for delta P, we use this, okay? Delta P, we have this expression, so we use that delta P in there, in the Z optimum expression. Then we can bring in Reynolds number. Why? Because the delta P has U infinity. So U infinity will, it will do something, and it will ultimately give you Reynolds number. Okay, some rearrangement. That again you have to check. And then there is a Prandtl number to the power minus 1 by 4 also. So this is only purely Prandtl number is a purely fluid property. Reynolds number depends on the flow also, because it has got that U infinity, which you are giving, right? You're running a fan or something and pushing the air into these channels. Okay, so this is Z optimum by L, which we obtained for forced convection case. Now before I complete this discussion, let me see whether I can show you something else or not. Yeah, so let me show you something like this. This is like a bit of a deviation from what we are doing now. But since we are talking about fin arrays, and I have been saying that fin arrays are used in various applications. For example, a motorcycle engine has a fin array, right? But a major application, major modern day application is electronic cooling. And this is very aggressive work, because the circuits become more and more integrated, and there's a huge amount of heat that these electronic components dissipate, and then they have to be carried away. For that, we have to have some arrangement. So maybe if you're lucky, that air cooling will work. Maybe you need something else also, right? So this is I thought this, we are not going to discuss this in great detail, but I thought just to give you some practical exposure, I picked up this from some other book, and this is also taken from this book by Krauss and Bar Cohen, which is Design and Analysis of Heat Sinks. So from the name, you can make out that this is a very practical applied sort of thing, right? Design and analysis of heat sinks. So what do we have here? We have a chip, and then there is some bonding material, and then we have some heat spreader. There's some there's some lead, there is some encapsulant, okay? And then you have, in this side, you have this heat sink. Okay, so the chip loses heat from this backside. There is a heat spreader also here. Not worry about heat spreader now, but this is heat sink, and there is a flow taking place, right? So if you want to analyze this, then people sometimes construct these sort of resistances. So these are thermal resistances. Thermal resistances you saw in undergraduate textbook. You have done those calculations, composite wall, this is resistance, then the next resistance, then the next resistance, like that. But this tells you that all this is useful in more practical applications also. So these are the resistances which is shown here. This is these are resistances. It says primary thermal resistances in a chip heat sink assembly, right? I think there may be people waiting outside, so I'll stop here for this class.